Hi, my name is Jim. Welcome to AC Review, and in this particular session we're not going to be discussing anything to do with phase angles or the impedances or the details you got into in AC circuits. We'll wait for power factor correction before we do that. So we're just going to look at this from the standpoint of some of the basics, especially taking into account power calculations. So to start with, I've got a clock here with a pendulum, and this is swinging back and forth from left to right, left, right, and what we know about a pendulum is it swings left, it's going to reach a point when it stops. And when it stops, the velocity is zero here. And the rise over run, the slope is zero. All the energy now is potential energy. It's not moving, so there's no kinetic energy. Then it starts to swing back toward the right, and in so doing it crosses the very, very center line of the clock, and at this point its velocity is the fastest in the negative going direction, or more correctly in the right going direction, and it continues on to the right side where it again eventually stops. That'll be down here where the slope is zero, the velocity is zero, and then it starts to swing back to the left again. And what this will do is trace a sine wave through time. So when you're thinking about a sine wave, it needs not be anything more difficult than that of a clock. Now I've got a nice little demonstration for that up on the internet here, the laptop. Let me hold it up so we can take a look at this. It's kind of nice that I don't have to be too interested in being professional here. But what you're looking at is a fixed length phasor that's rotating through time and generating a sine wave as it goes. Now this not only applies to mechanical systems, it also applies to electrical systems. Now I'm able to see sine waves in my head, and I suppose that I can do that because I've been working in electronics for many, many years, but it's a very desirable feature if you can do that. Now let's get into a little bit more detail here. Talking electrically now, we have voltage with respect to time, in this case equals 10 volts peak, you're being told that, times the sine of 2 pi ft. Now to solve this, if we wanted to know what the voltage would be at some point in time, we would have to have our calculator in radian mode to do that. So you have to remember that you do that, and the reason is that the argument of the sine wave has to be dimensionless. So if we take 2 pi, is what we have is a radian is a piece of pie, if you will, PIE, the kind you eat, where the radius is equal to the arc length, and there are approximately 57.29 degrees per radian. So if we wanted to fill up a unit circle with this, or one cycle, we would find that it would take 6.28 radians to do that. 2.68 pieces of pie, if you will, to fill in the pie pan, or basically 2 pi rads per cycle. So that's what we have here is 2 pi radians per cycle, and then we have F, which is in cycles per second. Now the old term for frequency used to be cycles per second, but it was abused by engineers and technicians. What's the frequency? 60 cycles. Well, 60 cycles per what? Hour, year, day? No, per second. So the word hertz means cycles per second. Finally, in our equation we have time, and if we look at the units, and this is the second time through this, so you see these canceled, but anyway, the units of cycles cancels out, and the unit of time cancels out, and what we're left with for the argument of our sine wave is radians, and that's a dimensionless number. So we can find out what the instantaneous voltage is if we wanted to know that. Now let me skip ahead here a little bit. I had a marker on this, but it fell off. Here we go. So starting with our sine wave again, we're going to let the frequency in this case be equal to 1 kilohertz, and what's very important is to know the period. Now, the period is capital T as opposed to time, which is lowercase t, and is simply equal to the reciprocal of the frequency. So the period for a 1 kilohertz sine wave is 1 divided by 1k, and that'll come out to be 1 millisecond, which on your calculators, which should be in engineering notation mode, would illustrate that as 1e negative 3. And that's the power of engineering notation, because it'll always give you an exponent which is can be evenly dividable by 3, meaning milli, micro, nano, pico, and so forth. So if it takes 1 millisecond to complete one cycle, what I know then is a half cycle is going to be 0.5 milliseconds, or 500 microseconds, and so forth. So I can get a pretty good idea of what the instantaneous voltage would be just by finding the period and marking off key pieces here. Negative guy, 750 microseconds. 90-degree point would be 250 microseconds. And that leads me into kind of pre-analyzing what kind of answer I should get if I'm looking for VFT. Contrarily, if we have the period and we want to find the frequency, all we would do would be manipulate this, solve for f, and f is equal to 1 over the period t. So the radiant frequency is in rads per second, and the radiant frequency is designated by omega. It simply equals 2 pi f. So if omega equals 377 rads per second, f would be equal to, and this is a little bit cluttered up here, 377 divided by 2 pi, and that'll give us 60 hertz, which is our power line frequency. I did this because of the units, and it turned out to be pretty messy. So the 60 hertz sine wave at your wall outlet is actually cutting through 377 radians per second. Finally, to find omega, if we know what the frequency is f, all we have to do is multiply by 2 pi. Thus, the radiant frequency would be 2 pi times 60 hertz, which would be 377 rads per second. So you very well might see some equation like this. V of t equals 169 sine of omega t. And you don't panic with this here, Volts peak, because omega is simply 2 pi f. 169 is the actual peak voltage at your wall outlet. So you need to be comfortable with going back and forth between radiant frequency and frequency in hertz, which is cycles per second. Now, going back here a bit, lay out of the way. Let's take a look at the next sheet here. Make sure. Now I've designated this voltage source and polar notation as 10 volts at 0 degrees V peak. And notice that the symbol of the sine wave has a plus or minus on it. Now what that means is that the way I have it connected from the standpoint of an AC circuit is that it's going to start in quadrant 1, move to quadrant 2, and so forth. If I had this the other way, with plus on the bottom, minus on the top, this would start opposite. Further, if there's a DC offset available, like you have in Multisim, and we added DC to this, or we have AC riding on top of DC, that is, just about any transistor amplifier, then this would be the polarity of the DC component. So we're not going to be worried about this. I just wanted to mention it while we're here. So let's talk about power a little bit. And we have here our voltage on this case, 10 volts. So we're going to go up to 10 volts peak, down to 0, and then down to negative 10 volts peak, and then back up to 0. And if we wanted to find what the power would be, all we would have to do is using P equals V squared over R is to do that. So in quadrants 1 and 2, when we're squaring the positive voltages, we would get a waveform which would look something like what we see in red. It's going to be a power cycle for the first two quadrants. Now in quadrants 3 and 4, V squared is going to be giving a positive number. So what we get is a repeat, basically, of what we see over here in red. Now, the red, I'm going to call it waveform. It's really not. You can't see this on a scope unless you have a math function. Means that a regular light bulb operating from 60 hertz is flashing at you at 120 times a second. So this is positive because of the squaring down here. So we get two of these power pulses, if you will, per second. Likewise, if you don't want to use V squared over R and you elect to put the current in, P equals VI. Here you have positive voltage, positive current in red, positive power. Negative voltage, negative current in red, positive power. So there's no reactive elements in this, it's just pure resistance. And we're not, like I said before, going to be getting into phase shifts just yet. Now let's take a little bit of a closer look at this in detail, and what I've done is I've sketched these power peaks for one cycle, which is shown in red here. And what we have here is 10 watts, and this is referred to as the peak power. It's going to be 10 watts. Sometimes the power is 0. Sometimes it's 1 watt. Sometimes the instantaneous power is 8 watts. So what we need to do is figure out what the average power is, and what I'm going to do is draw a line exactly in the middle of these guys. I'm going to put a hinge here, and then I'm going to take the top of this and rotate it to fill in the valley. Now, if we take SpongeBob for an example, and he has a hinge here, we would be rotating this until this fills in this. So what we end up with is the average power is going to be equal to 1/2 the peak power, which is 5 watts. Now this is true for one cycle or more of power. So in the conclusion we can draw from this here is that P equals P average equals 1/2 P peak. You have to know that. Now when you go to the store and you're looking for a 100-watt light bulb, you don't walk up to a clerk and say, I would like a 100 average watt light bulb. You don't say that. So if it doesn't have average in here, it's assumed that it is average. For example, just P means P average. So now let's take a look at RMS. So everybody, I hope, would kind of get the point here of rotating this, and it's, I think, a good graphic to show what is going on. The RMS voltage is the effective DC voltage which produces the same amount of heat in a resistor. And these experiments were done in the late 1800s. So the magic operator for this, which you must know, is 0.707 V peak, and this can be shown mathematically. Not interested in doing that. So if I wanted to find out the effective voltage of a 10-volt peak sine wave, I would simply multiply it by 707, which would give us 7.07 volts RMS. So P equals P average, and this is going to be equal to the voltage RMS squared divided by 10. So in the circuit on the previous page, that would come out to be 5 watts. So RMS voltage or RMS current is going to give you average power. That's in V squared over R or I squared times R. So we can also say, if we want to kind of prove that a little bit better, is that P equals P average equals the quantity, important, 0.707 times V peak squared, and when we square 0.707, guess what? We get 1/2. V peak squared equals 5 watts. So that's where this 50% comes from, is the 0.707 squared is 0.5. Now we can go further with that and say that the peak power would be equal to the peak voltage divided by the resistance, which is true, and the peak power would be 10 watts. Average power, 5 watts. So P average is equal to 1/2 of P peak, and contrarily, P peak is equal to 2 times P average. Now this is true only for sine waves. If we had a radar signal, what we would find is we would have an enormously high pulse of power and then a cooling off period. So the average power of, say, a radar at an airport would be very low, but the peak power would be enormous. And that's because it follows the inverse square law radio waves do. If you double the distance, you have to increase the power by a factor of 4. Then it hits an airplane and radiates back, double the distance, increase the power of 4. So to double the range of a radar, you have to increase the power by 16 times. A little bit off topic. So the important thing to note here is the relationship between peak and average power for sine waves. You should know that like this. There's no such thing as RMS power. It's average or peak. Average is formed by RMS voltage occurrence, and peak power is formed by peak voltages or occurrence. So here we see 5 equations that you really have to know. V peak equals 1 divided by 0.707 times V RMS, and I just memorized this 1.414, which is this term right here. So this guy is equal to 1.414, and that's the way you find V peak. And sometimes you need to know that. In power electronics, like where we are, it's good to know that because sometimes our capacitors charge up to the peak. And the breakdown across a diode relates to the peak in 2 dimensions. Stay tuned. So VRMS equals 0.707 V peak. Obviously you have to know this guy. V peak to peak equals 2 V peak. Not too much exciting there. If this is V peak, no offset, then the V peak to peak would simply be twice as much. P average equals P equals 1/2 of the peak power, and the peak power equals 2P average. So these 5 equations you need to be really familiar with and understand them. So, if we go on to the next guy, suppose we have this circuit, and I'm expressing this voltage here in polar notation, 10 volts at 0 degrees V peak. We have 2 resistors here, a 10K and a 7K in series, and what we want to do in this is to find VR2 and RMS and the power of resistor number 2 that is going to dissipate. So there's a couple ways to do this. We'll do both, and I'm going to start by finding the voltage across R2. So I'm going to do that using voltage divider. We start out 10 volts peak, same usual stuff, 10K over the total K gives us 4.11 volts peak. So the peak power is simply going to be the peak voltage divided by 7K, and that comes out to be 2.422 milliwatts peak. So here I'm using the peak voltage and I got the peak power. Now if I want the average power, piece of cake. Divide it by 2, 1.211 milliwatts. So I can use the peak voltage across this using voltage divider, or you can push currents too, but voltage divider is really truly simple, and determine from that the peak power, which leads directly by a simple division into the average power. So we can solve it a different way. VR2 we know is equal to 4.11 volts V peak. Now if we like, we can convert that directly into RMS. So all we would do to do that would be to multiply the peak by 0.707, and that gives us 2.91 volts RMS. Now this sets us up for the next calculation, which determines directly the average power. Why? Because I'm using RMS voltage. So P average, and I should say, I suppose out here, P equals P average equals the RMS voltage squared divided by the resistance 7K, and that comes out to be, as we would expect, 1.21 watts. If we wanted to know P peak, solving it this way, all we have to do is take P average and multiply it by 2, giving 2.41 watts peak. So that'll conclude the review part for AC circuits, and thank you for viewing.